If you need to travel a great distance, such as from one region to another, you book an airplane flight and anticipate being in the air for several hours. When traveling across space though, you must travel faster, because all of the things of interest are so far away. Space explorers have always been on the lookout for a technique to travel faster than light in order to reach deep space quicker. All of the methods revealed so far have serious flaws, but scientists have discovered a new approach. How does it function? What are the conditions? When will you be able to use it for travel? Welcome as we introduce a revolutionary method of traveling faster than light. Light is fascinating and crucial, since seeing this storyline would be tough without it. We can walk without running into objects because of the sun and various artificial light sources that humans have devised. However, you've probably heard that light travels quickly. But how fast does light travel? Kindly leave a like and subscribe to support the channel. Surprisingly, the exact speed of light is known and serves as the foundation for most other calculations. The speed of light in a vacuum is 299,792,458 meters per second, or 983,571,056 feet per second. In 1 second, light will travel around 186,282 miles. When you turn on a light bulb in a dark room, the light covers the space almost immediately, and you won't even notice that light travels. The light year is another unit of measurement that involves light. It is the distance that light can travel in 1 year. This figure is approximately 6 trillion miles, 10 trillion kilometers. Astronomers and physicists use it to measure vast distances across our cosmos. As previously said, the universe is so enormous that light can travel thousands of years from one end to the other. For example, light travels from the moon to our eyes in about 1 second, implying that the moon is 1 light second away. Nevertheless, sunlight takes longer to reach our eyes, taking roughly 8 minutes, implying that the sun is about 8 light minutes away. The light from Alpha Centauri, our nearest star system, takes about 4.3 years to reach us. Therefore, Alpha Centauri is 4.3 light years away. Other stars and things outside our solar system can be found anywhere from a few light years to billions of light years away. This is why what astronomers see in the far reaches of the universe is history. When they investigate distant objects, they perceive light that depicts the objects as they were at the time that light left them. While there are many amazing things that light can do, scientists have attempted to travel at the speed of light. This is fascinating, since humans will soon be an interplanetary species. For example, Elon Musk, the wealthy CEO of SpaceX, wants to establish a civilization on Mars, but his explorers will have to endure at least 5 months of spaceflight before touching down on the red planet. Depending on how close the two planets are, this might last up to a year. And what's without even considering the dangers it poses before landing on Mars? With speed of light travel, they can complete the journey in under 4 minutes. Researchers have tried a variety of approaches to create extremely fast travel. However, there was always a problem that no other approach could solve, until a scientist presented the new discovery we'll show you in this video. It's difficult to accomplish even 1% of the speed of light, which is still very fast because it can transport you from Los Angeles to New York in less than 1 second. In a specific word, the issue is energy. The movement of anything generates energy, which physicists refer to as kinetic energy. To accelerate, you must increase your kinetic energy. The issue is that increasing speed requires a lot of kinetic energy. It takes 4 times the energy to make anything go twice as fast. Increasing the speed of something by 3 times requires 9 times the energy, and so on. To accelerate a 110-pound teenager to 1% of the speed of light, for example, would require 200 trillion joules. That's about the same amount of energy as 2 million Americans use in a single day. Consider the EM drive, which was billed as a technology that would transport humanity to the farthest reaches of the universe in record time. Theoretically, this software technology works by trapping microwaves in a shaped chamber, where their bouncing produces force. The chamber is closed, so it will appear to move without any fuel input or force output from the outside. The EM drive is based on Newton's second law, which states that force is defined as the rate at which momentum changes. As a result, An electromagnetic wave, or EM wave, moving at the speed of light has a certain momentum that will transfer to a reflector, producing a little force. The EM drive, which sees simple yet turns our understanding of physics on its head, is enabled by this accumulated small force in large quantities. There is no energy moving in or out, which leads us to wonder how the waves begin to move, how they continue to move, and where the momentum comes from. Without an explainable push, you can't have spontaneous produced momentum, which is why so few scientists are interested in the EM drive. If the EM drive works, it calls into question a lot of what physicists think they know about the cosmos. Physicists at Dresden University of Technology put the EM drive to the test, revealing that the optimistic results obtained by NASA and the Chinese demonstrating thrust were all false positives explained by other forces. However, as Dr. Eric Lentz, a physicist with over 10 years of expertise in practical applications, has demonstrated, the warp drive holds immense promise. Lentz wasn't the first person to try to make the warp drive a reality, and not only in science fiction. Miguel Alcubierre, a Mexican mathematician, was the first to attempt it. His idea became the first formal literature on warp drives in 1994. Unfortunately, the so-called Alcubierre warp drive necessitates a massive quantity of energy, as well as the dreaded exotic matter as a co-ingredient. This highly radioactive substance is solely theoretical and has never been observed in nature, let alone manufactured by scientists. Since then, a few variations have been proposed, including a 2010 update to the physical design of the Alcubierre drive by former NASA engineer Dr. Harold G. Sonny White. His revision reduced the required energy to a more manageable level, yet it was still impractical because the method still required exotic matter, albeit in less quantities than the Alcubierre system. Another group of Swiss researchers known as Applied Physics, or APL, proposed their own idea. Amazingly, their warp bubble was created without the use of any exotic materials. Their model, however, was unable to move faster than the speed of light, which is the holy grail of space travel. To demonstrate how his approach differs from others already offered, Lentz begins by describing the physical structure of the classic Alcubierre drive, which is the foundation for practically all other solutions. The Alcubierre method, he claimed, gave an intuitive image of what a warp drive would do: constrict the space directly in front of the center region, housing the ship or vehicle, and expanding the space immediately behind it. This depicts the warp drive as a curved wave that a spacecraft will ride to its destination on. Despite the fact that it is the cornerstone of warp travel, Lentz contends that it is not even the most important aspect. Instead, he claims physicist Jose Notario's answer from 2002 demonstrated that the expansion and contraction were not required to move the ship ahead. That work led him to reconsider how a warp drive may be formed using simply ordinary matter rather than unusual materials. Notario demonstrated that the expansion might be simple or zero everywhere and still move a ship. This is a big accomplishment, since it eliminates the necessity for exotic matter, which warps the space in front and behind the theoretical passenger in practically all theoretical warp drive methods. Lentz produced his own variation based on Notario's idea, which he says is even more realistic because it is based on common physics. Aside from this important material distinction, Lentz claims that his solution differs geometrically from Alcubierre's and most others because of how the energy is distributed across the warp bubble. The energy density and curvatures are maximum separated in the Alcubierre solution, with the energy constrained to a tiny torus between the zones of intense contraction and expansion. In Lentz's proposal, the curvatures and sources are highly connected, with the regions of high energy density and high expansion and contraction virtually exactly overlapping. Because of the geometric differences between his concept and existing concepts, Lentz's proposal could be a more practical warp solution than those previously offered. In fact, Lentz's warp drive is still just a concept. He does, however, see a few immediate measures that may be done to bring his version closer to reality, one of which, like all previous drive hypotheses, is to reduce the amount of energy required. From here, where does Lentz plan to take his warp drive? He claimed the next goal is to use a modern-day fission reactor to create a warp bubble capable of traveling at 1% the speed of light. The physicist said he would consider patenting his warp drive, but he stressed that his work is just one piece of a larger, rapidly growing body of work in this field, and that the recent increase in new warp drive concepts since Alcubierre's 1994 proposal gives those in his field hope that a real, testable version may be closer than we think. It's been wonderful to see how far warp drive research has progressed recently, according to Lentz. He believes that many more advancements are possible, and he is looking forward to seeing what the next several years bring. Thank you for watching. Let us know your thoughts on the speed of light in the comments below.